This is AP Calculus 6-8, Part 1, Finding Antiderivatives and Indefinite Integrals, Basic Rules and Notations. And we're going to start going backwards today. We've learned how to take derivatives of all the different types of functions that we need to in calculus. Now we're going to learn how to go backwards. We're going to be integrating those same functions. So I'm going to show you how to do that using differentiation. We're going to take this function. Remember, the d over dx means find the derivative of 5x cubed. And we learned before that if we want to take the derivative of that, we're going to take the exponent times the coefficient, which is 15, keep the x, and decrease that exponent by 1. So 3 minus 1 is 2. So this is the derivative of that function. What we want to do now is go backwards. We want to think, what could we have started with to end up with this as the derivative? And the first thing you think about is, well, the degree has decreased by 1. It's always going to decrease by 1. So we're going to add 1 to the exponent every time. And then we need to think about how to get this number back to its original form. And so let me show you how to do that using integration properties. Your problems will look like this. This is the integration symbol, and we've talked about that a little bit already. Find the integral, or they're also called antiderivatives. Find the antiderivative of 15x squared dx. Now, this is the derivative of the original function. This right here still represents the thickness of the rectangles that have been supposedly drawn here. Now, we're getting into the part where we're not going to have to find areas anymore. We're not going to have to draw trapezoids or rectangles anymore. We will be able to do this pretty much algebraically if we know some basic calculus steps. So when you're taking the integral of an individual term like this, what you would do is you would take the variable, you would add 1 to its exponent, you're going to keep the coefficient, and then whatever your exponent is, you would divide by that same thing. So we have 15x cubed over 3, and if we simplify that, we get 5x cubed, which was our original. So to recap that, you're going to add 1 to the exponent and then divide the whole thing by what your new exponent is. Pretty simple. We're going to start out by doing monomials, integrate monomials, and then we'll move into polynomials pretty quickly because it's very similar. So anytime we're trying to integrate, we have to have our functions written as a variable to a power. So for this, I'm going to rewrite first, and you're going to see that you're going to have to rewrite quite a bit before you can take antiderivatives. So if I rewrite that, that's x to the 1/2 dx. And remember the rule, I'm going to keep the original variable. I'm going to add 1 to the exponent. Well, 1/2 plus 1, 1/2 plus 2 over 2 would be 3/2. So my new exponent is 3/2. I have to then divide by that same exponent, 3/2. So what I would do here is invert and multiply. So that would be 2/3 x to the 3/2. And if you do that, then you could go backwards and see if you got it right. You can check your answer very easily. So 3/2 times 2/3 is 1. X, 3/2 minus 1 is 1/2, which gives us the square root of x. And there's one thing I'm leaving out here that we need to talk about. Let's suppose I have an integral of dx. And understand the number in front of the dx is just a 1. What would I have had to have there to get a derivative of 1? Think about this. What about 5 dx? What would have to have been there in order to get a constant of 5 as my answer? Well, if you think about that, if we have a variable with an exponent of 1, and we decrease that 1 by 1, don't we have x to the 0, which cancels out? So if I have the integral of 1 dx, that would just be x, because if you think about that, x to the first, well, 1 minus 1 is 0. The coefficient was 1. The variable drops out. We're left with the coefficient. Here, that would be a 5x. We also need to think about what has happened if we had a function originally start out with some constants. I don't want to go any further before I introduce this because this is extremely important. If I have something like this, d over dx, find the derivative of 3x squared plus 10. Well, if you take the derivative of that, this term would be 6x plus, well, what happened to the 10? Well, constants, when we take the derivative of them, just become 0. So our answer here becomes 6x. Well, we have to account for that 0 because every single function that I've done so far could have had a constant added to it or subtracted from it, but just dropped out when we took the derivative. So we have to account for that for every single integration that we've done. So go back for the last couple that we've done, and what you need to do is understand that this could have had a constant that dropped out at the end, and if it did, we would need to have plus c. C stands for that constant that could have been there. Because if we take the derivative of this, we've already established that that would be x to the 1/2 or the square root of x. But if we take the derivative of a constant, it's dropped out. We don't know what that constant would be, but every single function that we have could have had a constant. So we have to account for that from now on when we're doing integrals. So go back in your notes, all of these integrals that we've done so far, put a plus c, because if you don't put plus c when it's an indefinite integral or just a basic antiderivative, you will get it wrong. It's going to look for that every single time. Now, we're going to move into a new section soon where we don't have to do that anymore, but there's a very specific thing you will have in the problem that tells you not to put that in anymore. So until you see that specific thing, until I tell you about that, every single one of these has to have a plus c in order to get them right. So let's look at this one. If I want to take the antiderivative, I'm going to keep the 1/2. That's going to be x to the 3 plus 1 is 4. And then I divide by the coefficient 4. If I do that, that's understood to be 4 over 1. I invert and multiply, so that would be 1/8. X to the 4th. And don't forget your plus c. You could double check, make sure when you take the derivative of that, you would get what you started with. So these are very easy to tell if you're getting them right or not. You can just do a real quick check. Here's another one where you're going to have to rewrite it. I can rewrite that to x to the negative 2 dx. I'm going to follow the same rule. I'm going to add 1 to my exponent and then divide by my new exponent. So that would be x to the negative 2 plus 1 is negative 1 over negative 1 plus c. So that would be negative 1, and then x to the negative 1 is 1 over x. So that's negative 1 over x plus c for my final answer. So what happens if we have the integral of 0? An integral of 0 could have been any constant. So the answer there, the integral of 0, is going to be c. Here, for this property, if you have a k is any number at all. So if you have that, like you had any number other than 0 left, then you know that you would have had an x in front. Now, we could say that this is 0x, but the x is going to drop out. So we would have 0x plus c, and we would just have a c when we have an antiderivative of 0. For this one, k is any constant, so it could be a 5, it could be a 10. So if you have a constant dx, the integral or antiderivative of k dx, that would just be kx plus c. An example of that would be the integral of 10 dx. The dx tells you what variable we were working with. So that would just be the antiderivative of 10 dx would be 10x plus c. The antiderivative of 5 dt, well, that would be 5t plus c. The dt tells us what variable to use. So that variable can be anything. It doesn't have to be x. It could be any variable. For this one, if we have k, a constant, times a function, that constant can be brought outside of the antiderivative symbol to make it easier. And sometimes you'll want to do that. For example, I might have something like this. The integral of 10x squared plus 5x minus 15 dx. Well, if you think about that, all of those are divisible by 5. So I could bring the 5 out and then rewrite it. That would be 2x squared plus x minus 3 dx. And then take the antiderivative of that. If we have a string of different functions together, they can be taken the derivative of separately, and that's kind of where this property comes in. The antiderivative of f of x plus or minus g of x, that's the same thing as the antiderivative of f of x plus or minus the antiderivative of g of x. And both of these would have a dx with them. So that's what we're doing here. We're going to take the antiderivative of each of these separately. I've just brought the 5 out first. So if I do that, I'll have 5 times, and then my answer would be, I'm going to keep the 2, add 1 to the x squared, so that would be x cubed over 3, plus x2 over 2 minus 3x. I have to have my plus c. And then if I multiply, I would have 10/3 x cubed plus 5/2 x squared minus 15x plus c. And understand the 5, you're multiplying the 5 by c to get 5c, but since the constant is an unknown anyway, if you multiply it by 5, it doesn't change anything. There's really no point to make it 5c, it's still a constant, so you just put plus c still. Now, if I'm doing this for real, I would probably not bring the 5 out. I don't think that's any easier, but there are going to be occasions where that would be easier to do. And you'll see some examples of that as we move forward. But if I were to do this without taking the 5 out, I would have a 10x cubed over 3 plus a 5x squared over 2 minus 15x plus c. And you can see it's the same thing. We did it probably quicker not taking the 5 out for that one, but I wanted you to see that it is the same thing even if you bring a constant out. And again, there will be times when that is easier to bring it out, but that's another lesson. And then this is what we've been doing this entire lesson. I'm just going to put it in symbols. If you have x to the n dx, that would be x to the n plus 1 over n plus 1 plus c would be my kind of a formula for an antiderivative. Okay, for a problem like this, this is an example of where it might be best to bring the coefficient out. I can bring that 5 out, and then if I take the antiderivative of this, the only way to do that right now, that would require something called the chain rule, but until we learn the chain rule, you're going to have to FOIL that in order to be able to take the antiderivative. We have to have it into several different terms, something plus something minus something, to get your final antiderivative. So if I FOIL that, I have x squared plus 4x plus 4, and that's a dx. And I'm going to take the antiderivative of each term. So that would be x cubed over 3 plus 4x squared over 2 plus 4x plus c. I don't need that symbol. Once I take the antiderivative, the symbol goes away, so I probably should put parentheses there. And then I would multiply the 5. So that would be 5/3 x cubed plus 10x squared plus 20x plus c for my final answer. And again, you may think it's just as easy to put the 5 distributed in first and not take it out. Whichever you want to do, you should still get the same answer either way. Something like this, we're going to have to rewrite it because there's no way, we don't have any rules, any kind of quotient rule like we did for taking derivatives. There is no quotient rule or power rule for antiderivatives. There is a chain rule, but there is no product or quotient rule. So if you see a quotient like this, what you're going to have to do is rewrite that. So if I have x plus 1 over, that's x to the 1/2 dx, what I have to do is divide that power into each of the powers up here. So that rewritten would be x to the 1 over x to the 1/2 would be x to the 1/2 plus 1 over x to the 1/2 is x to the negative 1/2. We've got that dx on the whole thing. That's just telling us what the variable is, and the thickness of the rectangles is very, very small. That would be x to the 1/2 plus 1 is 3/2 over 3/2 plus x to the negative 1/2 plus 1 is 1/2 over 1/2. We need the plus c. If we invert and multiply, we have 2/3 x to the 3/2 plus 2x to the 1/2 plus c. You could convert those back to radicals if you want to. You could leave it like this. Either one is fine. Here's another example where we have to simplify first. We cannot we don't have a quotient rule, so there's nothing we can do. We have to simplify it first or rewrite it first. So we would have 20x squared minus 5 plus 6x to the negative 2 dx. For the first term, if I rewrite it, that would be a 20x cubed over 3 minus 5x plus 6x to the negative 1 over negative 1. So we have 20/3 x cubed minus 5x minus 6 over x. And we need the plus c at the end. So you see this is a good introduction to the integral or antiderivative. You can do some practice and we'll go from there. Tomorrow we'll learn a few more tricks. We'll start with trig functions, things like that, because you need to go backwards with all the different types of functions that we've learned so far.